Now we're going to solve some examples for Newton's laws of motion. So the first example is a conceptual one. Um, Train cars are connected by couplers, which are under tension as the locomotive pulls the train. Okay, so we have a locomotive, there are couplers in between the cars, and we have tension on each of these couplers. Imagine you are on a train speeding up with a constant acceleration. So here's a constant acceleration A to the right. As you move through the train from the locomotive to the last car, measuring the tension in each set of couplers, does the tension increase, decrease, or stay the same? So we're moving from the locomotive to the cars, to the last car, and we keep measuring the tension on these couplers, T1, T2, T3. So is this tension increasing or decreasing as we move to the last car? Okay, so when I look at the free body diagram of the last car, I only see that it is under the influence of this tension T3 and it's moving with acceleration A. Therefore, I can say that the net force acting on this last car is T3, which is equal to its mass m times acceleration A. When I go to the next one, so this one, now I see that it is under the influence of tension T3 and tension T2. So the net force acting to the right is T2 minus T3, which is equal to mass times acceleration, because they're moving with the common acceleration. Now I already know that T3 was equal to ma, therefore T2 must be equal to 2ma. Now I go to the next one. The next car is here under the influence of T1 and T2. As you can see, the net force acting on this is T1 minus T2 equals ma. So therefore, I will see that T1 must be equal to T2 plus ma, which is 3ma. So I noticed that when I go from the last car to the locomotive, I keep measuring the tension on these couplers. I see that the tension keeps increasing. So therefore, I can conclude that T1 must be greater than T2, must be greater than T3. Therefore, when I move from the locomotive to the last car, from T1 to T2 to T3, I see that the tension on the set of couplers is decreasing. So let's write this observation. As we move through the train, from the locomotive to the last car, the tension in each set of couplers decreases. So T1 is greater than T2 is greater than T3. So when I go from the locomotive to the last car, the tension keeps decreasing. So this is a nice application of Newton's second law. The net force acting on each car must be equal to ma. So we have to identify the net force acting on the last car as the only tension that is to the right. And of course, I'm assuming that there is no friction here. So we neglect friction. We have this assumption. So the tension is the only force these couplers feel. So for the last car, it's T3. For the second car, second from last, it's T2 minus T3, and then the next one is T1 minus T2, etc. So the I can see that the tension keeps increasing from the last car to the locomotive, or decreases from the locomotive to the last car. Okay, so we're done with this example, so let's move on to the next example. Here we have two blocks, and we're going to consider the forces acting between the blocks. So let's start with reading the problem statement here. Two blocks of masses m1 and m2 with m1 greater than m2 are placed in contact with each other on a frictionless horizontal surface. A constant horizontal force F is applied to m1, so you can see this force is applied to m1 as shown, and there is a physical contact between m1 and m2. Find the magnitude of the acceleration of the system. Determine the magnitude of the force between the two blocks. So in these problems, the first task is to draw the free body diagram for isolated parts of the system. So let's start with M1. So let's call this y-axis. This is our x-axis. So this is x, this is y. Now I have to identify the forces acting on M1. So M1 is modeled as a particle, and we identify all the forces acting on it. On the y-axis, there is gravitational acceleration, so there is the weight. So we can say that first we should have the weight of M1, M1g, that is pointing down, and this is going to be opposed by a normal force that the surface is applying to M1. So we need to have a normal force N. Now we have this force F that is to the right, so we can basically draw a force to the right, and this is F. And then, because M1 is touching M2, there is the force exerted by object 2 on object 1. So this is the force F21. Object 2 exerts a force on object 1. So because the surface is frictionless, we don't consider friction. Those are the four forces acting on M1. Now, as a result of these forces, what is M1 doing? Well, on the y-axis, it's doing nothing. Acceleration on the y-axis is 0. Therefore, the net force acting on the y-axis, the y components, should add up to 0. So what are the y components? So let's call this normal force N1. So N1 minus M1g must be equal to 0. So N1, we can say, is M1g in j hat direction. That's the normal force. What is it doing on the x-axis? On the x-axis, it has a certain acceleration a, and therefore the net force on the x-axis, or the sum of the x components of all the forces, should add up to m1 times acceleration a. And we have a force to the right, F, in I hat direction, and F21 in minus I hat direction, minus F21. This is equal to M1A. So let's keep this result in mind. F minus F21 is equal to M1A. Now, we can look at the free body diagram for M2. So let's again note our coordinate system here. This is the y-axis, this is the x-axis. M2 will be modeled as a particle, so we have a single particle here. There is a force acting on it to the right, which is the force exerted by object 1 on object 2. So there is the weight m2g, which is pointing down. There is the normal force that opposes the weight n2, and there's no friction. So those are the three forces acting on this particle with mass m2. F was acting on m1, not on m2, but the force exerted on m2 is due to object 1. So F force exerted by 1 on 2. So what is m2 doing as a result of these forces? It doesn't have any acceleration on the y-axis. So the net force on the y-axis is 0. Therefore, n2 minus m2g is 0. The normal force it feels, n2, is m2g in j hat direction. So once again, this is our I hat direction, this is our j hat direction, this is j hat, this is I hat, the unit vectors. So we can write it in terms of the unit vectors. Now what about the x component of the acceleration? It's moving with the acceleration a, therefore the net force acting on the x-axis must be equal to m2a due to Newton's second law. There is only one force. Force exerted by 1 on 2 is equal to m2a. So let's also keep this result in mind. So if I go back to the previous free body diagram, F minus F21 is equal to M1A. So I write this equation, F minus F21 is equal to M1A. And F12 is equal to M2A. So if I add these two equations, what would I find? Since F12 is equal to minus F21 as a vector, so they have the same magnitude. This is Newton's third law. Newton's third law, action-reaction. So we can see that when I add them up, these two would cancel, and I will find that this force is responsible for the common acceleration of m1 plus m2. F equals m1 plus m2a. Therefore, the acceleration a can be written as a vector f divided by m1 plus m2 in I hat direction. Then I go back to the problem statement, find the magnitude of the acceleration of the system. The magnitude of the acceleration is f divided by m1 plus m2. All right. Now, I could look at this problem from an alternative point of view. Alternatively, we could consider m1 plus m2 as a single system. So, alternatively, we could model m1 plus m2 as a particle. And in doing so, we can draw the free body diagram. Now, there is the normal force, there is the weight, and there is the force F acting on it. So here is our particle. There is a force F acting on it. There is a normal force. There is the weight m1 plus m2 g, and this is our particle with mass m1 plus m2. And this has an acceleration on the a-axis. So therefore, the net force on the x-axis, F, must be equal to m1 plus m2a, because ax is equal to a. So this brings us to the same conclusion about the common acceleration. Now part B asks me to determine the magnitude of the force between the two blocks. So let's talk about the magnitude of the force between the two blocks. I can use F12 or F21. F12, if I go back to this free body diagram, here is m2 times a. So F12 is m2 times a. Now I know what a is. So it is m2 times f over m1 plus m2. So I can say that the magnitude f12 is equal to magnitude f21, but they point in opposite directions. And it can be written as the force F multiplied with m2 divided by m1 plus m2. So this would be my final answer for the magnitude of the contact force between these two blocks. Okay, so let's summarize what we said about this. We have two blocks with masses m1 and m2 in contact, m1 greater than m2. They're placed in contact. There is a contact force developing here. They're on a frictionless surface, so the surface has a coefficient of friction equals 0. Horizontal surface, a constant horizontal force F is applied to the right as shown. We want to know the magnitude of the common acceleration and magnitude of the contact force. So we have drawn free body diagram for M1, which gave us a relationship between F and F21, force exerted by object 2 on object 1. F minus F21 is M1A. We have drawn the free body diagram for M2, which told us that there is only F12, force exerted by object 1 on object 2 on the x-axis, which is responsible for its acceleration. So it's F12 equals M2A, and summing them up, we find the common acceleration F over M1 plus M2, or alternatively, we consider M1 plus M2 as a single system with a net force F acting to the right on it. So this gives me the common acceleration right away, easier method. And since F12 is equal to M2A, or I can use F minus F21 equals to M1A, these equations basically substituting for A, F over M1 plus M2 give me the result F times M2 over M1 plus M2 as the contact force. Well, let's move on to another example. A 3 kilogram object is moving in a plane. Okay, so we have a mass 3 kilograms moving in a plane with its x and y coordinates given by x is equal to 5t squared minus 1. So position as a function of time is given, and y is equal to 3t cubed plus 2, where x and y are in meters, SI units, t is in seconds. Find the magnitude of the net force acting on this object at t is equal to 2 seconds. Now, because we're talking about force, we need to know the acceleration. Now, the acceleration has an x component, ax, which is the second derivative of x, d square x, with respect to time, d square x dt square. So what is the second derivative of x? Well, it's the derivative of the derivative. So 5t squared minus 1 has a derivative 10t. So I take one more derivative. I obtain 10.0 meters per second square for ax. So this tells me the net force Fx has an x component, mass times acceleration, which is 3 times 10, 30.0, because I'm in SI units, newtons. Now I look at the y component of the acceleration, ay. That would be second derivative of y position with respect to time. So that's the derivative of the first derivative, 3t cube, has a derivative 9t square. So this would be 9t square. The next one is a constant that doesn't have a non-zero derivative. So taking one more derivative, 9t squared becomes 18t in meters per second squared. T is in seconds. And the net force on the y-axis is mass times y component of the acceleration. That is 18 times, what is the t? Well, we're looking for the force at t is equal to 2.00 seconds. 18 times 2 times, so that is our acceleration times mass. Mass is 3 kilograms. So that gives us 108 newtons. What is the magnitude of the net force? So we can calculate the net force whose x and y components we have determined has a magnitude square root of fx squared plus fy squared. That would be square root of 30 square plus 108 square. So this gives us 112 newtons. So this was a simple exercise to determine the magnitude of the net force acting on an object at a certain point in time, knowing its position x and y, or r as a function of t, for a 3 kilogram object. So we just take two derivatives to find the acceleration components, we find force components, and we can find the magnitude using the components of the force. Okay, so let's move on to the next example. All right. Now in this example, we have a bag of cement whose weight is Fg hanging in equilibrium from 3 wires as shown in the figure. So there's the wire 1 that has a tension T1 making an angle θ1 with the horizontal, and wire with tension T2 making an angle θ2 with the horizontal. Assuming the system is in equilibrium, show that the tension in the left wire T1 can be written in terms of the gravitational force, or the weight Fg cosine θ2 divided by sine θ1 plus θ2. So it's given by this expression. Now I will start with the free body diagram for cement. And let's first establish our coordinate system. So here is our x-axis, here is our y-axis. We will look at cement as a single particle, and we write the forces acting on it. There is tension T3. The third wire exerts a tension T3, and there is the weight of the cement, which is pointing down, Fg. Now, as a result of these two forces, what is the cement doing? Nothing. It's in equilibrium. Ay is equal to 0. Therefore, the net force acting on the y-axis must be equal to 0. T3 minus the weight must be equal to 0. So T3 must be equal to Fg, the weight of the cement. Now, I have a massless point here. You can see that is the point, the joint between the 3 wires. It's a massless point. And I'm going to draw a free body diagram for this point. So this point feels the tension T3 pointing down. there is the tension T2 that is making an angle theta 2 with the horizontal. So this is the angle theta 2 it makes. The same angle appears here, theta 2. And there is T1, which is making an angle theta 1 with the horizontal, theta 1 or theta 1 here. So these are the three forces acting on this massless point. The net acceleration on the y-axis is 0, therefore net force on the y-axis is 0. So what is the net force acting on the y-axis? That is T1 sine theta 1, the component of T1 on y-axis, T2 sine theta 2, and T3 is pointing down, so it's minus T3. This must be equal to 0. Acceleration on the x-axis is also 0 because it's not moving. The net force on the x-axis is 0, so we can write T2 cosine theta 2, that is in plus I hat direction, minus T1 cosine theta 1, T1 cosine theta 1 in minus I hat direction must be equal to 0. So I have this equation between the tensions, I have this equation between the tensions as well. Now, let's put the story together. We have first found that T3 is equal to the weight of the object. Now we can utilize this information in the equation that we have obtained here between T1, T2, and T3. So this equation will become then T1 sine theta 1 plus T2 sine theta 2. It was minus T3, which is minus Fg. This is equal to 0. On the other hand, from this equation, T2 cosine theta 2 equals T1 cosine theta 1, we can write T2 cosine theta 2 equals T1 cosine theta 1, and therefore where we see T2, we can substitute T1 cosine theta 1 divided by cosine theta 2. So putting this together, we have T1 sine theta 1 plus T2 sine theta 2. For T2, I substitute what I have found here, T1 cosine theta 1 multiplied by sine theta 2 divided by cosine theta 2, and then minus Fg equals 0, so this is equal to Fg. So if I take this into T1 parentheses and also make a common denominator, this will be in T1 parentheses cosine theta 2 sine theta 1, so sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2 divided by cosine theta 2, that is equal to Fg. Now at this point we have to remember a trigonometric identity. What is sine of theta 1 plus theta 2? This is sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2. So we can note this from our trigonometry. So this was an important trigonometric identity. So using this identity, we can write T1 times sine of theta 1 plus theta 2 divided by cosine theta 2 is equal to Fg. So we can write T1 as the weight Fg cosine theta 2 divided by sine of theta 1 plus theta 2. If we go back to the problem statement, look for the expression we were supposed to prove. That's exactly what was suggested in the problem statement. Okay, so in summary, we have worked on a bag of cement which was hanging from 3 wires and it was in equilibrium. So we have determined the relationship between the tensions on these wires, and we did that by looking at the free body diagrams for the cement and for the joint point between the 3 wires. The free body diagram of the cement gave us T3 equals Fg. Free body diagram of the joint gave us no acceleration on the y-axis, T1 sine theta 1 plus T2 sine theta 2, y components minus T3 equals 0. And so if you want to plot these forces here, this is the force T1, this is T2, and this is the force T3 acting on this joint, which is acting in the opposite direction on the bag of cement. And there is the gravitational force Fg, which is the weight. So we show these forces on the free body diagram, modeling these as point particles. And for the condition of equilibrium on the x-axis, having no acceleration on the x-axis, T2 cosine theta equals T1 cosine theta 1. By manipulating these 3 equations, substituting for T3 Fg and substituting for T2 T1 cosine theta 1 over cosine theta 2, in this equation we obtain T1 in terms of the weight and the angles theta 1 and theta 2. Okay, let's move on to the next example. When 2 objects of unequal mass are hung vertically over a frictionless pulley of negligible mass as in figure, the arrangement is called an Atwood machine. The device is sometimes used in the lab to determine the value of g. Determine the magnitude of the acceleration of the 2 objects and the tension in the lightweight string. Okay, so we will look at these objects as points. So here is the free body diagram for M1. So M1 is modeled as a point particle. It feels the tension T1 that's pointing up, and it has a weight M1g that is pointing down. And this is the y-axis. So we can say that the net force on the y-axis must be equal to T1 minus M1g, which is M1a. Now I go to M2. M2 is modeled as a point particle. It feels the tension T2 pointing up. It feels the weight M2g pointing down, and the net force on the y-axis must be equal to M2a, because it's accelerating in as you can see, this wire is rotating in the clockwise direction. That is shown as the positive direction for acceleration here. So we have T2 minus M2g is equal to m2a. Now I want to also concentrate on this top point. So this top point is a massless point, and for that top point, if I look at the forces acting on that point, I see that there is T1, which is to the left, and T2, which is to the right. So here is T2, here is T1, and because this part has no mass, m is equal to 0, net force acting on it is mass times acceleration. Mass is 0, so it's going to be net force equals to 0, which tells us that T2 equals T1 equals T. So the tension on this string is the same on the left side and on the right hand side as well, because we have a lightweight cord. So this is a consequence of having basically a lightweight cord that is used in this Atwood machine. So it's a lightweight string. So that gives us the conclusion that the tensions are the same. Now, we can substitute this result into the two equations we have obtained from the free body diagrams. So we can say that T1 must be equal to T2 to a common tension. And when I substitute that result into this equation, T1 minus M1G equals M1A, that equation will become T minus M1G equals M1A. The second equation was T2 minus M2G equals M2A, so that would be T minus M2G equals M2A. Now, I noticed that there is a mistake here because the acceleration is pointing down. So if I call this acceleration of this object M1 positive, so you can see that acceleration is pointing up here in plus j hat direction. So here in this case the acceleration is pointing down, so it's actually the weight m2g minus t2 equals m2a, or if you write it this way, t2 minus m2g, then as a vector you can see that this acceleration is minus m2a, because the acceleration is pointing down. So this we have to be careful here with the direction of acceleration. On the right hand side it's pointing down, on the left hand side it's pointing up. Okay, so with that correction we can see that this is going to be minus m2a, because as a vector equation this is t j hat minus m2g j hat equals minus m2a j hat. So it's actually a vector equation. So we add these two equations. The first thing I can do is multiply the second one with minus 1. So minus t plus m2g plus m2a. And the tensions will cancel when I add them up. So I will obtain m2 minus m1 G equals m1 plus m2a. So this is going to give me, for the acceleration of the system, m2 minus m1 divided by m1 plus m2. So this is the magnitude of the acceleration. It's pointing down on the right hand side, pointing up on the left hand side. Okay, so when m2 is greater than m1, you can see that this is going to be the scenario. A will come out as a positive quantity, so we have the correct scenario here. Now, how about the tension? Well, the tension, I can use the first equation, T minus M1G equals M1A. So I can say T is equal to M1G plus M1A. So this would be M1G plus M1A would be M1 M2 minus M1 square divided by M1 plus M2 G. So this can be written as M1 square plus M1 M2 plus M1 M2 minus M1 square divided by M1 plus M2 G, putting everything in G parentheses, plus M1 square and minus M1 square cancel. So we find that we can write the tension as 2 M1 M2 divided by M1 plus M2 times G. That's the tension on the string. Okay, so in this problem, we're talking about the Atwood machine. We have two objects of unequal mass hung vertically over a frictionless pulley. Pulley has negligible mass. We also have a lightweight string. This is sometimes used to determine the value of G in the lab. We want to know magnitude of acceleration and tension. Tension is already the magnitude of the force acting on the string, as you know. Free body diagram for M1 gives us two forces, T1 pointing up and 1G pointing down. For M2, T2 pointing up, M2G pointing down. For the top point, we have T2 pointing to the right, T1 pointing to the left. And I realized that because I have no mass at the top point, it's a lightweight string, T1 and T2 are approximately the same. So there is a single tension T. For M1 free body diagram, I obtain net force acting on Y, T1 minus M1G is M1A, where A is pointing up. So this is direction-wise correct equation. And for the free body diagram for M2, it is T2 minus M2G. If I write it this way, because the acceleration is pointing down, it is equal to minus M2A. So T2 minus M2G equals minus M2A. Putting these three equations together, I find the common acceleration magnitude M2 minus M1 over M1 plus M2. This is going to be the case when M2 is greater than M1. The system will be moving to the right, or M2 would be going down and 1 would be going up. So that scenario would be correct and A would be positive, as you can see here. And the tension can be obtained from this equation or from this equation. I find it to be 2m1 m2g over m1 plus m2. When I substitute for acceleration, the result we have found here. Okay, let's move on to the next example. Example 6. Now we have an inventive child named Nick, who wants to reach a tree, an apple on a tree, and in doing so we have an important setup here that he is utilizing. So we're going to talk about this setup. Okay, now an inventive child named Nick wants to reach an apple in a tree without climbing the tree. Sitting in a chair connected to a rope that passes over a frictionless pulley. Here's a frictionless pulley. The string is passing over it. Nick pulls on the loose end of the rope with such a force that there's a scale here, spring scale, that reads 250 newtons. So this is reading the tension on this part of the string. Nick's true weight is 320 newtons and the chair weighs 160 newtons. Nick's feet are not touching the ground. There is no contact force between the ground and Nick. Draw one pair of diagrams showing the forces for Nick and the chair considered as separate systems and another diagram for Nick plus chair as one system. Show that the acceleration of the system is upward, find its magnitude, find the force Nick exerts on the chair. Because there's a contact between Nick and the chair, we're going to talk about a contact force. So let's start with drawing the free body diagrams. Now once again, we're modeling Nick as a single particle. So here is Nick considered as a single particle. And what are the forces acting on Nick? Well, first of all, Nick has a weight. So we have a mass of Nick times G. Now, Nick is sitting on this chair, so the chair must be exerting a normal force on Nick. So we have to have a force exerted by the chair on Nick, FCN. And because Nick is holding the loose end of the string here, there will be the tension Nick will feel. So there is the tension T that is on the string, which is basically read by the spring scale. Now we can talk about the chair as a single particle. Here's our chair. The chair has a weight, mass of the chair times G. The chair feels a force because the chair is in contact with Nick. Force exerted by Nick on the chair, and I look at the chair and I see that the chair is in contact with Nick. It has its weight and it's also in contact with this string here, so it's also going to feel a tension T. Because we talked about this before, it's the same tension that appears on Nick and the chair because we have a lightweight cord here. And if I consider Nick and the chair as a single system, now for Nick plus chair, I can basically isolate Nick plus chair. So let's quickly do this. Nick plus chair is here. So this system feels 2T pointing up and the total weight pointing down. So we're going to have tension T, tension T pointing up, and the total weight pointing down. So there is T, 2T, and the total weight, mass of Nick plus mass of chair times G. So that was the first part of the problem. We have drawn a pair of diagrams showing the forces for Nick, chair, and Nick plus the chair. Now we want to know the common acceleration of the system. Now I start with the combined system. For the combined system, Nick plus chair, free body diagram, I can see that T plus T, 2T that is pointing up, so this is my y-axis here. 2T is 250 newtons times 2, 500 newtons pointing up. That T was read by the spring scale, remember, it was 250 newtons. So it is 500 newtons acting up. What is the total weight? Mass of Nick plus mass of chair times G. Nick has a true weight of 320 newtons. The chair weighs 160 newtons, so it is 320 plus 160, 480 newtons. Now I see that 2t pointing up is greater than mass of Nick plus mass of chair times g, the total weight pointing down. The system must be accelerating up because there is a net force pointing up. The system accelerates upward in the upward direction. Now, what is this acceleration? From the third free body diagram, the net force acting on y is 2t. The net force acting down is the total weight, which is the total mass times the acceleration a. So 500 newtons minus 480 newtons is equal to, the total weight is 480 newtons. So 480 newtons divided by gravitational acceleration g is the total mass times the acceleration a. So we find that acceleration a is 20 times gravitational acceleration divided by 480, which is the gravitational acceleration g divided by 24. That is roughly 0.408 meters per second square, because gravitational acceleration we can take to be 9.8 meters per second square, that is pointing down. Okay, so we have found that the system accelerates upward and the common acceleration is 0.408 meters per second square. What is the force Nick is exerting on the chair? Okay, so let's work with free body diagram for the chair. The second free body diagram. This gives us the tension T pointing up minus the force Nick exerts on the chair minus the weight of the chair is equal to mass of the chair times its upward acceleration. So we can see that this is going to be 250 newtons tension minus 160 newtons weight of the chair minus the force Nick exerts on the chair is equal to its mass 160 divided by g, mg equals 160, multiplied by acceleration. Acceleration was g divided by 24. So we can find the force Nick is exerting on the chair to be 90 minus, because these g's will cancel, 90 minus 40 over 6. So we can find the force Nick exerts on the chair to be roughly 83.3 newtons. Okay, so this was a good example of identifying forces on different parts of the system and looking at the system as a whole. And we also have to be careful with who is touching who. So there is nobody touching the ground. The chair and Nick are touching, so there's a contact force between them. Nick is pulling on the loose end, so Nick feels a tension. The chair is attached to the string as well, so chair feels a tension. Nick plus chair feels 2t pointing up, the total weight pointing down. So all of these forces were recognized in the free body diagrams. Then for the combined system of Nick and chair, because 2t was greater than the total weight, we see the system accelerates upward, and using 2t minus the total weight equals total mass times the acceleration a, net force on y is equal to total mass times a. We can find a here. And for the contact force, we can use the second free body diagram. T minus Fnc minus mcg is equal to mca. the mass of the chair times acceleration, where mass of the chair is found by, since we know its weight, 160 divided by g, A was g divided by 24, we can find this force to be 83.3 newtons. Now, let's work on one last example. Now, what horizontal force must be applied to a large block of mass capital M, shown in figure, so that the 10 blocks remain stationary? These will remain stationary relative to M, so they will move all together. M1 and M2 will not move with respect to capital M. Assume all surfaces and the pulley are frictionless. Notice that the force exerted by the string accelerates M2. Okay, so as usual, we will start with free body diagrams. So let's consider the combined system, capital M, M1 and M2 all together. So this is modeled as a single particle. So this single particle feels a force F to the right. There is the weight pointing down, which is capital M plus M1 plus M2 times G. And there is the normal force exerted by the horizontal surface, because it's touching this horizontal surface. It's going to be a normal force. So this is the particle with mass M plus M1 plus M2 feeling all of these forces. So this is going to be the x-axis, this is going to be the y-axis. And when I write the net force on the x-axis, it is just F. And that is responsible for the common acceleration M plus M1 plus M2 A. So I find that the acceleration of the system to the right must be the force, horizontal force F divided by capital M plus M1 plus M2. Now I'm going to look at the free body diagram for M1. Now M1, we have to be careful. You can see it's touching capital M. So the forces acting on M1 modeled as a particle, well, of course, it has a weight M1G. There's going to be the tension on the string, tension T, that's pointing up. So there will be the tension T here. And there is the force exerted by capital M on M1, which is normal to the surface. So capital M exerts a force on M1, F, M, M1. The net force on the y-axis must be 0. Why? Because I don't want M1 to move with respect to capital M. So this will be guaranteed by having T minus M1G equals to 0. So the tension must be equal to M1G. On the other hand, the net force on the x-axis must be equal to M1A, which is the common acceleration of the total system, combined system. So this tells me that force exerted by capital M on M1 must be equal to M1A. Now, when I go to the free body diagram for M2, I'm going to talk about the tension it feels. So assuming a lightweight string, again, it's the same tension here. There is the normal force and there is the weight. So three forces will be drawn for the free body diagram. So we have the weight M2G. There is the normal force acting on it due to capital M, and there is the tension to the right. Now, what is the net force on the x-axis? It is tension T that is responsible for M2A. So we have tension equals M2A, and remember that A was found as M2 F divided by capital M plus M1 plus M2. So I substitute this result, and this is going to give me also the tension T must be equal to M1G. So this must be equal to M1G. So M2 times F over capital M plus M1 plus M2 equals M1G. I can isolate F here. So F can be written as M1G times capital M plus M1 plus M2 divided by M2. This is the horizontal force F we have to apply so that M1 and M2 are stationary. So you can see, note that M1 and M2 are stationary with respect to capital M, since they move with the same acceleration. AX is equal to A and AY is equal to 0. The motion is on the x-axis, so they must have a common x component of acceleration and no y component of the acceleration. So working on the free body diagram for the combined system, I find that this acceleration, common acceleration, x component, must be equal to F over M of M plus M1 plus M2. From the free body diagram of M1, being careful about the contact force between capital M and M1, I see that there is the force exerted by capital M on M1 that is responsible for M1A, and the net force on Y must be equal to 0 because M1 cannot be sliding with respect to capital M. And for M2, I have the normal force, the weight, and the tension. And it was also mentioned in the problem that it's the force exerted by the string that accelerates M2. So tension is equal to M2A. So that which was also found to be M1G. So this gives us the horizontal force we need for the common acceleration on the x-axis and no acceleration on the